Right now, inside the blood vessels running through your body, glucose is moving through your bloodstream. Tiny molecules, invisible to your eyes, but absolutely essential to your survival. Your brain needs glucose, your muscles use it, your organs depend on it. Every time you eat carbohydrates, digestion breaks those carbohydrates down into glucose. That glucose enters your bloodstream, and for a short time, your blood glucose rises. That's normal. Your body expects it. But here's the important part. Glucose isn't supposed to stay floating around in your blood forever. It needs to get inside your cells. Because your bloodstream is basically the delivery highway. Your cells are the destination. And controlling that delivery is one of the most tightly regulated processes in human metabolism. Now imagine we follow one glucose molecule. It moves through the bloodstream, passes a red blood cell, and approaches a muscle cell. But there's a problem. The glucose can't simply walk through the cell membrane whenever it wants. The cell needs a signal, and that signal is called insulin. So where does insulin come from? Follow the bloodstream back toward the abdomen. The camera pulls out. Liver, stomach, small intestine, and behind the stomach, the pancreas. The pancreas is more than a digestive organ. Inside its tissue are specialized groups of endocrine cells, and among them are the beta cells. These cells produce insulin. Now, the glucose concentration in the bloodstream rises. The beta cells detect the change. Insulin is released. Thousands of insulin molecules enter the circulation. Now return to the muscle cell. Insulin reaches the surface. It binds to its receptor, and that receptor activates a chain of signals inside the cell. In muscle and fat cells, this helps bring glucose transport proteins such as GLUT4 to the cell surface. Suddenly, the cell becomes much better equipped to take glucose out of the blood. Glucose enters. The cell can use it. Blood glucose begins returning towards its normal range. This is the system working exactly as it should. Glucose rises. Insulin responds. Cells take up glucose. Blood glucose comes back down. Simple, but incredibly sophisticated. And when this system begins to fail, that's when the story changes. Because diabetes isn't simply a story about eating sugar. It is a story about metabolic regulation breaking down. And the first question is, what happens when insulin disappears?
Return to the pancreas. But this time, something is wrong. Zoom into the pancreatic tissue. Find the beta cells. And now introduce the immune system. Immune cells begin attacking the body's own beta cells. The cells responsible for producing insulin are being destroyed. This is type 1 diabetes, an autoimmune disease. The pancreas gradually loses its ability to produce enough insulin. Now follow the consequences. Glucose enters the bloodstream after a meal. Blood glucose rises, but there is no adequate insulin signal. Move to the muscle cell. Glucose is outside. The cell isn't receiving the normal insulin signal required for efficient glucose uptake. So glucose remains in the bloodstream. More arrives. And more. Blood glucose continues rising. This is fundamentally different from type 2 diabetes. In type 1, the central problem is insufficient insulin production, because the insulin-producing beta cells have been destroyed. That's why people with type 1 diabetes require insulin replacement. Without insulin, the body cannot properly regulate glucose metabolism, and the consequences can become dangerous very quickly. But now, we're going to look at the other major form of diabetes, because type 2 begins differently. Return to the pancreas. This time, the beta cells are still there. Insulin is still being produced. The hormone enters the bloodstream. It reaches the muscle cell. It binds to the insulin receptor. But something has changed. The cell isn't responding normally. This is insulin resistance. The signal is present, but the response is weaker. Imagine insulin knocking on the door. The door still exists, the key still fits, but the message isn't being transmitted as effectively. So the pancreas tries to compensate. It produces more insulin, more signal, more pressure. For a while, this can actually work. The pancreas is fighting to keep blood glucose within range. And this creates one of the most dangerous features of early type 2 diabetes. You can have metabolic dysfunction before your blood glucose looks dramatically abnormal. The body may still be compensating. The pancreas is working harder. But eventually, compensation can fail. Blood glucose begins climbing, first into the range of prediabetes, and eventually into diabetes. The important point is this: type 1 and type 2 can produce the same final problem, elevated blood glucose. But the biological route to get there is different. And in type 2 diabetes, the story becomes even more interesting. Because now we need to ask, why did the cells become resistant to insulin in the first place?
Move underneath the skin. At first, we see subcutaneous fat, but keep moving deeper into the abdominal cavity. Around the internal organs, we find another type of fat, visceral fat. And here's something important. Fat isn't simply passive storage. Adipose tissue is biologically active. It communicates with the rest of the body. It releases fatty acids and signaling molecules. And when excess adiposity develops, particularly visceral adiposity, the metabolic environment can change. Inflammatory signaling can increase, fat metabolism can become abnormal, and insulin signaling can become impaired. Now return to our muscle cell. Insulin arrives. It binds to the receptor. But the intracellular signaling pathway isn't responding as efficiently. The cell takes up less glucose. More glucose remains in the bloodstream. The pancreas senses the problem, so it produces more insulin. For a while, the system survives. But this creates a metabolic tug-of-war. The pancreas is pushing harder, the cells are responding less, and eventually, the pancreas may no longer be able to compensate indefinitely. Beta cell function can decline. Insulin production can become insufficient for the body's needs, and now blood glucose rises even further. This is why type 2 diabetes isn't simply you ate too much sugar. The biology is much more complicated. Genetics matter, age matters, family history matters, physical activity matters, body composition matters, sleep and other health conditions can matter. And the exact causes of insulin resistance are not completely understood. But here's the encouraging part. Some of the factors influencing metabolic health are modifiable, and one of the most powerful tools isn't sitting in a pill bottle, it's your muscles. Because muscles have a remarkable relationship with glucose. Now watch what happens when they contract. The muscle cell begins working, energy demand increases, and glucose uptake can increase through pathways that are not entirely dependent on insulin. Your contracting muscles can pull glucose from the bloodstream, even while insulin signaling is impaired. This is one reason physical activity is so metabolically powerful. And with regular exercise, the muscle adapts. Mitochondrial capacity can improve, glucose handling can improve, insulin sensitivity can improve. The tissue becomes metabolically more efficient. So exercise isn't simply about burning calories, it's changing how the machinery inside your cells behaves. But there is another major misconception we need to eliminate. You cannot do abdominal exercises and command your body to burn only visceral fat. Fat loss doesn't work like that. When body fat decreases, your body draws from multiple fat stores. But visceral fat is metabolically active and can respond substantially to overall weight loss and physical activity. And that matters because reducing excess body fat can improve insulin sensitivity and metabolic health. But what happens if insulin resistance continues and glucose remains elevated for years? That's where the real damage begins.
Return to the bloodstream. But this time, the glucose level doesn't come back down properly. It stays elevated, not just for a few minutes after a meal, but repeatedly, day after day, month after month, and eventually, year after year. This is where diabetes becomes dangerous, because glucose itself isn't the enemy. Your cells need it, your brain needs it, your muscles use it. The problem is chronic hyperglycemia, blood glucose remaining too high for too long. Now zoom into the inside of a blood vessel. At first, everything looks normal. Blood flows smoothly through the vessel. But persistent high blood glucose can contribute to damage in blood vessels and the tissues they supply. And once the vascular system begins suffering, different organs can begin paying the price. Follow the blood toward the eyes. Now enter the tiny vessels supplying the retina. These vessels are extremely delicate. They provide the retina with oxygen and nutrients. But diabetes can damage these small vessels over time. Abnormal leakage and other vascular changes can interfere with vision, and in advanced disease, vision loss can occur. Now follow the bloodstream again, this time toward the kidneys. Zoom into one of their microscopic filtering structures. Your kidneys are constantly filtering your blood,
but this filtration system depends on an intricate network of tiny blood vessels. Chronic diabetes can damage these structures. One early warning sign can be abnormal amounts of albumin appearing in the urine. As damage progresses, kidney function can decline, and in severe cases, kidney failure can occur. Now leave the kidneys. Follow a nerve. Move closer. Even your nerves depend on a microscopic blood supply. Diabetes can damage the small vessels that supply nerves, while metabolic injury can also directly affect the nerves themselves. This can lead to diabetic neuropathy, tingling, burning, pain, numbness, and eventually, loss of sensation. Now imagine a person steps on something sharp. Normally, pain immediately sends a warning signal to the brain. But if sensation has been reduced, that warning may be weak or completely absent. A small wound can go unnoticed. And because diabetes can also affect circulation and healing, that small injury can become much more serious. Now pull the camera back. The entire cardiovascular system appears: heart, brain, arteries, blood vessels. Diabetes also increases the risk of cardiovascular disease, including heart disease and stroke. And suddenly, we can see the bigger picture. This story started with glucose inside the bloodstream, a molecule your body actually needs. But when glucose remains elevated for years, the problem becomes much bigger than a blood sugar number. It becomes a problem affecting the entire body: eyes, kidneys, nerves, heart, blood vessels. And here's what makes diabetes especially dangerous. The damage can develop silently. You may not feel your blood vessels changing. You may not feel your kidneys struggling. You may not know that nerve damage has begun. The body can look normal on the outside, while the biology is changing underneath. But there is one final question. If type 2 diabetes develops through this long metabolic process, can we actually change the direction? Can the cells become more sensitive to insulin again? Can blood glucose return to a healthier range? And can diabetes sometimes enter remission? That's where the final part begins.
Return to the pancreas. Return to the bloodstream. We've seen how diabetes develops. Glucose rises, insulin responds. Cells take up glucose. But in type 2 diabetes, the cells become resistant to insulin. The pancreas tries to compensate, until eventually that compensation may no longer be enough. So can the system change? For type 1 diabetes, the situation is different. The immune system destroys the insulin-producing beta cells. The body can no longer produce enough insulin. That's why insulin replacement is essential. But type 2 diabetes gives us another possibility. Because the body can still produce insulin, there are ways to improve how the system responds. Regular physical activity can increase glucose uptake by working muscles. Exercise can also improve insulin sensitivity over time. Reducing excess body fat can help as well, especially when visceral fat decreases. Nutrition, physical activity, weight management, and appropriate medical treatment can all play a role. And medication may be necessary. Depending on the person, treatment can include metformin, GLP-1 receptor agonists, SGLT2 inhibitors, and sometimes insulin. Medication isn't a failure, it's treatment for a biological disease. But here's the fascinating part. Some people with type 2 diabetes can improve their metabolic health so much that their blood glucose returns to the non-diabetic range without diabetes medication for a sustained period. This is called remission. Not necessarily a cure, because the underlying risk can remain. If metabolic health deteriorates again, diabetes can return. So the real goal isn't simply making one blood test look normal. It's changing the biological environment that produced the problem. Now pull the camera back. The pancreas, muscles, liver, kidneys, heart, nerves, blood vessels, all connected by the same bloodstream. And now we can see the bigger picture. Diabetes isn't simply too much sugar. It's a failure of metabolic regulation. Glucose is the fuel. Insulin is the signal. Your cells are the destination. When that communication works, the entire system stays in balance. But when that communication breaks down, the consequences can spread throughout the body. And that's the real lesson. Diabetes may begin with glucose in the bloodstream, but its consequences can reach almost everywhere. This is BodyCode.